Okay, the next talk is by Vibha Srivastava. Thank you. A microwave processing of lunar soil, please.
Yeah, thank you very much. Good afternoon, everyone. So the topic for my talk today is microwave processing of lunar soil for supporting long-term exploration missions on the moon. It's a part of my PhD project at the Open University. Here is the content of my talk today. I'll introduce the topic. I'll talk about the challenges associated with microwave processing, and then I'll highlight the key research areas that I've identified so far in my literature review. Out of those key research areas, I'll give a brief on dielectrics, and then I would give an example of future application and conclude my presentation. So my topic broadly falls in the domain of space architecture with in situ resource utilization, as we have heard from the morning that mass is a critical component for any space launch, and if we can use the local or in situ resources for construction, we can cut down the cost of an expensive rocket launch. So what I'm trying to do here is I'm trying to investigate the existing lunar resources for constructing human habitats or landing or launching pads or equipment on the surface of moon by the use of additive manufacturing technique. Additive manufacturing technique, which is also commonly called as 3D printing, is a technique of fabricating a structure by building the layers, binding them, using a specific binder, which could be a chemical or it could be a heat source. Usually, for construction on Earth, we use water as a binder. Yes, we have found water on moon, but it is not that abundant at every location. And in case, in future, we come to know that there is sufficient amount of water present, if we can use some other form of heat source as a binder for construction on moon, we can leave that water as an in situ resource for using it as a life support consumable or even for propellant manufacture. And for that reason, we are looking for other form of heat sources that can bind the layers and fabricate a structure using 3D printing. The potential lunar resource on the surface of moon for construction is the lunar regolith. Regolith is any loose heterogeneous material which covers the surface of any planet over the solid rocks. I'll talk a little bit in detail about both of these. Let's see once again about 3D printing. The different methods that can be used to prepare the in situ resources for 3D printing could be either to extrude the slurry of regolith, melt the regolith, or sinter it. Sintering is a process where the material is subjected to temperatures below the melting point so that it joins with the nearby grain size particles and forms a solid. The heat sources that are available on the surface of moon for either sintering or melting the regolith are solar energy, nuclear energy, or electromagnetic radiation energy like the microwave. The 3D printing techniques, which can use these binding methods and fabricate a structure, could be fused deposition modeling, selective laser sintering, microwave or solar melting, or sintering. Out of these, I'm putting an effort to understand and investigate the microwave processing. And it is due to the fact that the lunar soil acts as a dielectric and readily couples well with the microwave. Now, there's a unique property in the lunar soil which lets it couple well with the microwave, and the key of that property lies in the lunar geology. Lunar surface is abundant in silicate minerals. The part of regolith, the lunar regolith, which is less than 1 centimeter in size, is called the lunar soil. And it is this part of regolith which is considered an ideal feedstock for microwave processing. The unique property which helps the lunar soil couple with the microwave is the presence of many nanophase-sized iron particles on the surface of moon. It is assumed by many researchers that this is the cause that the lunar soil can couple quite well. Metals in general reflect microwaves, but in their powdered forms, mixed with dielectrics like particles in air, can readily absorb the energy. So let us look into microwave processing. The microwave radiation, as we all know, falls in the electromagnetic spectrum where the wavelength ranges from 1 meter to 1 millimeter and the frequency is 0.3 gigahertz to 300 gigahertz. In my literature review so far, I have identified that many researchers have actually melted the lunar soil, the real lunar soil from Apollo missions, and the lunar simulant. But they have found some challenges associated with it. There is a weak absorption of microwave energy up to 200 degrees Celsius for the lunar simulant JSC-1A, and after the temperature of 200 degrees Celsius, it starts absorbing the microwave quite strongly. Another issue is that the microwave is preferentially absorbed by the inner portion and the surface stays less heated. And due to these factors, many researchers have proposed to combine the microwave heating with some other form of radiant heating using susceptors. The other area where not much research has been done to find out the other frequency in the microwave range where we can heat the lunar soil efficiently. Till now, the researchers have only worked with the kitchen microwave frequency, which is 2.45 gigahertz. The absorption of microwave energy by any material depends on three basic parameters: the power density, heating rate, and the half power depth. And the equations of these parameters are influenced by something called dielectric properties of the material. And for this reason, understanding the dielectric properties of lunar soil also becomes a key factor in my research. From here, I would like to highlight the three key research areas that I have identified so far in my literature review to address the challenges of heating the lunar soil at 2.45 gigahertz and test heating at other frequencies, to determine the dielectric properties of lunar soil and the factors affecting them, to test the strength and endurance of the finished product fabricated by microwave processing of the lunar soil for micrometeorite and radiation damage protection. Today, I'll briefly talk about the dielectric properties. So let's see what dielectrics are. Dielectrics are basically insulators. As we all know, when exposed to electromagnetic field, they get polarized. The two most important dielectric properties are dielectric constant and dielectric loss. Dielectric constant relates to the permittivity of the material, and permittivity of the material is the capacity of the material to get polarized in response to an applied electric or electromagnetic field or stored charge, which is the same concept used in capacitors. The dielectric constant is the ratio of permittivity of the material to permittivity of vacuum. An efficient dielectric supports varying charge with minimal dissipation of heat. And from there comes the concept of dielectric loss, because dielectric loss is a form of loss which is generated in the material by movement of charges in response to an applied electromagnetic field when polarization switches direction. And it is this loss which is used in our kitchen microwave to heat the food. The dielectric properties prominently depend on the frequency. Apart from it, they also depend on the density, mineral composition, grain size, moisture content, and temperature at which the material is subjected to. A work carried out by Olhoft and Strangway studied the dielectric properties of the real lunar soil samples collected from Apollo missions to analyze it up to the first 100 meters of the moon by testing at frequencies from 0.001 gigahertz to 1 gigahertz, and some samples were even tested at 9 gigahertz. They tried to establish the relationship of dielectric properties with the density. They also found out that the density varies with the depth as well. The density did increase with the depth, but below the depths of about 1 meter, they commented that the results were quite unrealistic. When they looked at the dielectric constant, they found that the dielectric constant increases with increase in density. The dielectric constant is commented to be not varying much with frequency above few kilohertz below the temperature of 200 degrees Celsius. They did not do much analysis on the chemical composition dependence on dielectric constant, but however, they tried to study the effect of ilmenite content on dielectric constant, and they found that with the increase in ilmenite content, actually there is no significant increase in the dielectric constant. But they also commented this does not mean that ilmenite is not having an effect, because increasing the ilmenite definitely increases the density, and which in turn affects and increases the dielectric constant. When they looked at the loss tangent, they found that the loss tangent appeared to be primarily increasing with the ilmenite content and secondarily in turn with density. They commented the loss tangent is considered to be varying with frequencies above 0.0001 gigahertz, but not much analysis was done. Another work carried out by Kala and Rathore talked about the dielectric properties of JSC1A, the lunar simulant, at 4 different microwave frequencies: 1.7, 2.5, 6.6, and 31.6 gigahertz. They tried to do the tests at temperatures ranging from minus 190 degrees Celsius to 200 degrees Celsius, as the lunar day and night undergoes such extreme temperature ranges. And they tried to establish the relation of dielectric properties with the temperature. The results were quite interesting. With the increase in temperature at all 4 frequencies, the dielectric constant and the loss factor both increased. But with the increase in frequency at a certain temperature, both the values decreased. So these 2 papers tell us about how the dielectric constant is dependent on density, temperature, and frequency. I need to further research upon and look into how the dielectric constant can vary with the grain size and the mineral composition, and in case, of course, we know there is water on moon, so in case how it changes with the moisture content. I would like to highlight here that understanding the dielectric properties helps engineers to feed the data back and find the values of power density, heating rate, and half power depth to see how well it couples with the microwave for construction purposes. And at the same time, the dielectric properties also gives a knowledge to scientists for designing active and passive sensors for remote sensing applications of lunar geology. In conclusion, I would like to give an example of a future application. It's a work carried out by Dul and his colleagues who studied few aspects related to the establishment of a lunar base for a crew of 10 with an accompanying astronomical telescope at the north pole of the moon. They proposed to set a lunar liquid mirror telescope, which is also envisioned by many researchers as a successor to James Webb Space Telescope. They state that the primary goal is to set up a permanent human presence, but the secondary goal is to utilize the base for high-value scientific research. Under the lunar urban planning, they propose that apart from construction of the lunar base, the telescope, and the power stations, the construction of roads leading to these bases, connecting them, and the landing and launching pads are also very important for the settlement. And they propose to do the construction by the use of microwave sintering of lunar regolith. Apart from the construction of roads and landing pads, they also propose to cover the lunar base with minimum 2 meters of lunar regolith so that it can give protection against the radiation damage and micrometeorite on the surface of moon. With this, I would conclude by saying that understanding and investigating the microwave processing is beneficial for both scientists and engineers to understand and further colonize our nearest neighbor, the moon, and go beyond it. Thank you very much.
Excellent. We have time for a couple of questions. If Manuel could stand by.
Thank you for the very interesting talk.
Thanks.
So Larry Taylor, as you know, says that the nanophase iron is very important for coupling with microwaves, and that's absent from simulants. Have you thought about doping simulants in some way to give it the equivalent of nanophase iron? Have you considered the differences in the maturity of the soil? Some have, more mature soil has more nanophase iron, and also, do you think there's a chance you might get actual lunar soil in your research?
Yes, thank you very much for the question. As you correctly mentioned, the lunar simulants do not simulate the nanophase-sized iron particles. And yes, some research has been carried out at ESA actually to dope it with ilmenite and see how it is changing the properties. So I'll be doing similar kind of research. I'll first test the basic lunar simulant, and then I'll try to dope it up with ilmenite, or even we will try to look for adding some susceptors like silicon carbide to see how the heating is improved. And sorry, I forgot the second question that you said.
Might get real lunar soil.
Yeah, I have to prepare a good case for that. If I'm able to, I hope I will get it. Yeah, that'll be really excellent for my research. Thank you.
Excellent. Do we have another question? If not,
Sorry, just as I've got the microphone, I suppose an alternative to applying for actual Apollo soils would be to obtain lunar meteorites, which are more readily available, and then ground them down as Phil was grinding down things to make a powder. I don't know whether that might be possible.
Yes, I think that's a very good suggestion actually. We would look into it. That would not get nanophase, but yeah, I mean that would take me a little bit more closer to lunar soil.
Hi.
Sorry.
Have you done any tests with other materials, or will you be doing, or just focusing on the lunar regolith?
Thanks for the question. I've not started any experiments, but I'm focusing on lunar regolith. So I'll be conducting the experiments with lunar regolith only. And if I am successful in reaching my objectives, and if I have time, I might look into going beyond moon and looking into Martian regolith as well.
excellent. So let's thank you again.